Hi everyone. In the second example, we will build two DC motor model. It's linear, but we can thread the UKF just like this one. Okay? It's a nonlinear method, but we can apply easily on the DC motor model. Okay? So I can copy all of these things. This is the DC motor implementation. We have some basic or the common points about these terms, and so this remains the change, but this is changed with the DC motor parameters, just like this one. The J is equal to 0.01, C is equal to 0.1, and KV is equal to 0.01. Our model is that the J times theta dot plus C theta dot, which is equals to what? KV UT. Okay, UT is the what? Is the R PWM rate. Okay, so the control input must also be given in here. Control input U is equals to what? The 50 times one length of T. Okay, this is the constant control input. Okay, so the x-true state is assigned with what? The 0. It's still also the position and velocity value, and also this is 1, and this may be equals to 1 e over minus 5, e over minus 5, and also this is equal to 1 e over minus 1. Okay, this is the same, this is the same, this is the same, and also this is the same, this is the same, and the initial estimate is start with the what? The 0 and 0. Okay, this code is more portable or the scalable for the other applications, right? And so in this case we need to define the new state space in here, x true 2. Okay, and also this is equals to what? The KV times U K minus 1, right, minus C times X true, these are the dynamic true 2, and also divided by J. Okay, and so this is the same, and also this is X true, and the measurement is the same, and also sigma points are the same at the prediction step, but we need to build to the what? The process model, just like this one. X1 G1 I, and X2 is the velocity value G2 I. Okay, and X dot can be equalized with the what? X2, and also the KV times U K minus 1 minus C times X2 divided by J. Okay, and so the chi prat is the same, this is the same, this is the same, and after that the whole algorithms are the same with the another one, because these are the update algorithm. If we using the prediction step key, which we must in here, we just only change the chi and these true simulation parameters in here. The rest of them is the same with the another one. Okay, and after that this is the time, this is the position of the what? The radian in here, and true position, estimated position, and the measured position in here, and also we have the what? The true velocity and the estimated velocity value, but this is equals to what? The radian sec. Okay, and so if we run this code, and then we will have this kind of operation here. Just see that if we put what? The 50% PWM rate, and so we have the 5 radian second velocity rate in here, and also we have these results, and also we need to give the what? The grid on in here, and the grid on in here. Okay, but we don't have any noise values in here, just like this one. And so in the first place, we need to increase the process noise, just like this one. 100 is given in here, and so we don't change anything in here, just like this one. But see that we have some basic noises in here on the what, on the measured position, but it's still too small. And so if we increase the values of the Q, and so we may have some the noises on this signal. But if we change in this one, just like this one, and so we can block the signals. See, we have some deflection rate on these values, and see that the true velocity values is built with with this denomination, but our estimated position is still correct. This is the powerful method for for the estimated velocity value on the DC motor based on the position one. And so this is the process noise, and after that we can increase the 10 times R value, the measurement noise in here, just like this one. And so the R signal right now is broken. See, we have the broken results, but our estimated position still without the noises values. This is a flat signal, but the other one is is fluctuated. And so if we increase the R values, R values with the increased values rate of these terms, and so we have some broken true velocity value, but still we have the good results. And so if we increase the measurement noise, just like this one, 10 times, and so the R measured position is given in here, but see that the estimated position is still correct and is still closing to the true position one. Okay, and so if I increase the R values, just like this one, and so we have too much noises on here at the position value. This is unrealistic, but even if this is unrealistic, we have the good results on the UKF filter. And also this one, see, 5 is still going on in here. But if I choose increase too much Q noises in here, just see that we have some deflection rate on the true position one. See, the green line is the true position, but we have too much noises on this system, and so our estimated position still is good enough to emulate our model response in here, just like this one. Okay, because we utilize the cheap process model in here, because we have these dynamics values in here. In the real-time application, we can close these values, but in terms of these signals. And so if we increase too much this one, and so see that the R green positions, which is given in here, just like this one, but the R estimated signal is now broken. See, this is realistic, but the measured signals unrealistic in here. And also if we increase the too much R values in here, and so the R signal is given in here, but the R model cannot be changed, or cannot be still to estimate this value. But just see that the position is 100-200 radian, and so this algorithm is now cannot be run, because it's not the idealistic results, it's a theoretical results. But we don't have any kind of position, even if the theory we don't have any deflection, so 102 radian to the 200 right radian. Okay, but this is the absurd case for the R algorithms. But if we choose the process noise, and this one is given in here, and see, we have the great value on this time. See, this black line is is our basic results, and so we can easily estimate the values of the velocity in here. Just see that. Okay, and so in the next lesson we will talk about the parameter estimation based on the UKF filter based on this nomination.